Morning, everyone. Welcome to our last day of IAMA. Thank you for being here. Thank you for all the conference organizers for putting together a really great couple of days. I'm here glad to present two installments of our final session. The topic here is simulating the formation and physiochemical properties of particles in the atmosphere at regional and global scales. This remains a considerable challenge to this date. In addition to the efficient algorithms to represent complex aerosol processes, detailed model evaluation is needed with respect to multiple features of particle properties that affect their impacts on climate and health. So here we are going to present recent advances in regional and global scale modeling of particles relevant to climate and human health, development of computationally efficient algorithms to represent these processes and models, as well as their evaluation with laboratory and field measurements. I'd like to point out that unfortunately, our session co-chair, Knut van Salzen, was not able to come to this meeting in person, but he was quite active in the scoping of the session and selection of speakers and active throughout the process. So I thank Knut for his participation, and hopefully he'll be able to join us for another meeting in the future. With that being said, it's our pleasure to introduce our first invited speaker. Dr. Simone Tilmes is a project scientist 3 at NCAR and co-chair of the Community Earth System Modeling Chemistry Climate Working Group. Her scientific interests cover the understanding and evaluation of chemical, aerosol, and dynamical processes in chemistry climate models, which includes investigation of the ozone hole, tropospheric chemistry, aerosols, air quality, long-range pollutant transport, stratospheric aerosol injection, hydrology, sea ice, and solar radiation management. So pretty much everything. She's been modeling all of the things for quite some time. And of all those things, today she's here to tell us about the comparison of sectional and aerosol, or sectional and modal aerosol schemes in CSM2 for injection experiments. So let's give her a warm welcome.
Thank you and good morning. My name is Simone Tilmes, and I guess this is so I will talk about comparisons between a sectional and modal aerosol model in CSM. And I also will talk about some application of this for future aerosol injection experiments or geoengineering, since this is a new topic that's more and more discussed. I want to thank my co-authors listed here, and thanks for inviting me to this conference. It has been fun so far. And so what I'm using is the Community Earth System Model, or CSM. And this is an Earth system model, so that means it couples really different components. It can couple land, atmosphere, ocean, sea ice, carbon cycle, and so on. And so this model can be run in different configurations with fully coupled ocean, or just also with notched meteorological met fields, so focusing on aircraft campaigns or other things. What I'm using is 2 atmosphere configurations, the WECM, or Whole Atmosphere Community Climate Model. This is a configuration that goes all the way to 140 kilometers in the vertical. So we're resolving the stratospheric dynamic quite well as comprehensive chemistry. And then I'm also talking about ChemChem, which is more focusing on the stratosphere and the troposphere, comprehensive description of chemistry, as well as aerosols, secondary organic aerosols. Our default model is the modal aerosol model. And so what we did in the recent few years, we implemented a new model in this that can be fully substitute aerosols, like the model, which is the community aerosol radiation model for atmospheres. This is both an aerosol as well as a cloud model. We use the implementation that Peng-Fei Yu in 2015 has described. So we use an aerosol model that is having 2 groups, mixed aerosols as well as pure sulfates. And we're resolving 20 bins for each of these groups. So again, what we did was we really replaced this modal aerosol model. We went through all the different configurations in the atmosphere, chemistry, radiation, and clouds, removal and emissions. And what we're working on right now at NCAR is also something that we call a new flexible aerosol interface, that you can easily actually put all the aerosol information in this aerosol interface. And then what you can do is much easier communicate with the atmospheric components and changing aerosols. So it's not all intertwined like it was in the past. This is work in progress. So this model was also to be implemented because we have funding from NOAA to look at stratospheric aerosol interventions or geoengineering and building more suitable aerosol model for this. So what we now looked at and ran was different versions of CSM. When we designed the WECM middle atmosphere version with the CAMA model, this is running on 2 degrees. It's really focusing on the stratosphere, full stratosphere chemistry, but reduced troposphere chemistry and SOA description. While we also produced a version of ChemChem with fully interactive chemistry in the troposphere and 1 degree, so we can look at interactions also with the climate and other things. What you can see here is a table that shows kind of, we added, I don't know if I can point, maybe, does that work? Oh, this way? Well, yeah, maybe briefly. Okay, so well, the first 2 rows show the CAMA model, and we actually adding quite a few number of aerosol tracers, but we still can afford running this fairly well. So it actually is suited similarly to our most comprehensive working model without CAMA. So we can run some longer simulations, which is promising. So the first thing we did was evaluating the model on the Mount Pinatubo period. This is the WECM middle atmosphere model results. You can see the glossec data here after Mount Pinatubo from January to March. So this is an average from January to March 1992. We're injecting a default amount of 5 teragram S or 10 teragram SO2 in 1 point. And what you can see is that the MAM model is about reproducing this aerosol distribution. But it's in all models and recent evaluations that all the models kind of put the aerosols more to the northern hemisphere and not getting this extra layer in the southern hemisphere in like 20 kilometers. And so when we ran CAMA that way, we also see much fewer aerosols. So we were wondering what's happening. But then we played around with more regional distributions. And we're really in this paper that is describing it. It's a GMD paper now, 2023, Tilmes et al. is showing that when you do regional injections, you get much better distribution. You also get aerosols more into the southern hemisphere since we distribute initial injection 5 south to 50 north and a spread higher altitude. And we think that's just simply needed when you have global models. You cannot just dump everything in one grid box because things you have OH depletion, you don't get the formation, and especially in CAMA, we are lacking in the process of coagulation at that point. So, I mean, not lacking, but it's reduced compared to MAM. So anyways, when you actually run these 2 model versions, we did various tests. We also tested different nucleation schemes in CAMA, VCPs, VCPs, and we can really reproduce the observations with CAMA quite well. Even better if we increase the aerosol injections to more reasonable values that are actually known from literature and from observations. And so, yeah, you basically can use both models. So that looks good, right? Why use CAMA? But if you look at the size distributions, you do see that what you can see here is balloon observation from Wyoming and Black Points. We can see in green, the WECM, the MAM size distribution. And then the bars in blue is the pure sulfate CAMA bins, as well as the red mixed sulfate bins. And we're doing quite well in reproducing the size distribution better than MAM. If you look on the right, this is the volume distribution. And really, we are representing the larger masses better than the model can do this. And you can also see that we're kind of saturating in the last bin. So we're thinking that we may have to improve still our model to get a larger range in the pure sulfate to cover things like Mount Pinatubo, but also for stratospheric aerosol injections. We did also evaluate background distributions in a similar way. We're really doing well, I would say, within the error ranges of the data set. But again, we can see that our CAMA model, the sectional aerosol model, is reproducing the balloon data quite well. And then we did comparison to ATOM. We picked the data that are in the stratosphere, which are not that many, but you still see that really the smaller sizes are overestimated with MAM, as well as the larger spin. So we can, I think that the CAMA model is serving as a nice benchmark here. We did an evaluation in the troposphere, and I don't know, I don't want to spend much time since it's a short presentation, but the main point is that we're doing quite well in MIM and karma. One thing is that we noticed at the top, bottom left, if you look at the tropics, it's 6 to 12 kilometers. We added secondary organic aerosols to the karma model, and we can see that the bins are just starting too large. We don't really cover the Aiken or accumulation nucleation that you would think have to be covered with secondary organic aerosols. So we're piling up in the smallest bins over there. I wish I could point, I don't know. Oh, there we go. Here. So that's something, again, just work in progress. This was the first step. Now, we also ran a free running RECM model. So we do fixed sea surface temperatures. We're quite excited that we can reproduce, again, stratospheric aerosol observations. We also compare to the URBI data in terms of radiation at top of the atmosphere. And what you can see is that the karma model, what we did was we run a double radiation call with and without the aerosols to see what's the effect on the radiation. And the blue line, which is the karma aerosols, is doing quite well to reproduce these URBI data. So we are quite satisfied. We think this is the model we can use now for stratospheric aerosol injection experiments while we're still developing it. So the next step is really to do this. And I want to a little bit introduce stratospheric aerosol interventions. The idea is to increase aerosols in the stratosphere to reflect a little part of the sunlight in terms of cooling the surface, right? And countering some of the impacts of global warming. But the idea is not to replace mitigation at all. As you can see in the black line, this is a business as usual scenario. We're not going to I mean, that's kind of the consensus. You really have to do as much mitigation and decarbonization as possible. And maybe climate intervention, maybe something you can do when you just want to basically decrease a remaining increase in temperatures, like the peak that goes over some temperature targets, and do some SAI, phase it in, phase it out for some time. But of course, there are strong requirements, at least for us as researchers. We do need to make sure strong decarbonization is set in place. You have to have governance and ethical requirement in place. There's actually a nice session at AGU that will discuss this. And we need to have a comprehensive understanding how well do models actually do, what are the impacts, and how can we reduce uncertainties. And so if you inject a certain amount into the stratosphere, you get changes. Sulfates, especially heat. If you do other aerosols, it may not be so much, but you get a strong heating if you do a lot of aerosol injection. This is the case that we did a lot of aerosols. You get changes in water vapor, changes in zonal winds, in ozone. This all feeds back also to the climate. So you more aerosols you need. Obviously, the side effects could be larger. And then we did in the WMO ozone assessment and evaluation of how much heating do we produce with a certain AOD that is from the aerosol injections, and you can see different models. They are all over the place. They are a factor of 2 different. So there's a problem because we don't know what's the right answer, but that's important to judge the impact. So is it differences in aerosols? Is it differences in resolution? Is it difference in chemistry? And so what we have, we also look obviously at the cooling of aerosols because that's what you want to do. So how much cooling can we achieve with a certain amount of aerosol injection? What you can see is that there is between different models a factor of 2 differences. One type of model says we only cool 0.4 Kelvin with 10 teragram continuous injections with time. And other models say it's more like 1.3 Kelvin. That's a huge difference, right? And it does give us an uncertainty how much aerosol do we need, economical aspects, all these things depend on this. So what are the reasons for this? And we are looking at aerosols here. So there was a paper by Weisenstein et al. 2021 that had various experiments. I'm just pointing out a few. There are lots of lines here, but I want to focus right now on the solid line. With your injections, 10 years, continuously 10 years of SO2 injection of 5 teragrams sulfur. This is a sulfate distribution. You see the injection area, you see the distribution. When you do it with different models, you get very different aerosol burdens. The modal model with CSM shows much more aerosols than a sectional aerosol model, so-called, than another modal aerosol model. So we want to really explore what's the differences. They also did experiments with H2SO4 injections. And in addition, they did experiments with, instead of injecting at a region, they injected in points. You get different distributions. You can differently manipulate how much cooling you get in this way. But the end question is really here, why do we see all these differences and what is causing this? So what we did, I just talked to you in the first half of the talk. We have now a comprehensive model that you can run both modal and sectional aerosol model. And so we ran that and there's also SO2. So we did this now, and this looks on the red line is the burden of the first experiment with SO2 injections of a regional injection as well as point injection. So the red line is the main model, and the blue line is now the CAMA model. So this is a consistent model framework. That means we have the same resolution, same physics. So that clearly points to differences that if you have a different aerosol model, you do get different answers in the burden. So looking at the size distributions, again, similar to what we evaluated earlier, you can see here the main is the modes in green, the 3 modes for sulfate, and then CAMA model. And what you can see is that they're really different in terms of, first of all, CAMA can better reproduce the nucleation because the modes for MAM just cover the icon mode somewhat. And also the bin or the mode is very narrow for MAM4. So we cannot resolve with MAM4 the larger sizes that occur when you inject more particles. For CAMA, we will lose more mass. If we have more mass in the larger spin, we get more deposition, we'll get these differences. And since we have evaluated the model before, we're thinking that CAMA is probably the more reasonable model here. But again, we see that we probably have to increase still some bins for the pure sulfate mode to, to represent that even better. But still, this shows that a different aerosol model can give you very different answers. We did the same for the H2SO4 injections. I didn't talk much about it, but what that really is, it means that we are injecting in the accumulation phase H2SO4. So assuming that an aircraft could do that, and that usually helps to produce more aerosols or a larger burden. And when you use the different aerosol models here, modal versus sectional, again, you see this difference between those. When you do regional injections, however, if you do point injections, that's actually more similar. So the sizes, you can learn something about where are the discrepancies between those two models. Looking at the size distribution again, we really do not resolve in the model these larger volume or masses, and that results here in much smaller burden for the CAMA model. And even though we have a very similar distribution in the burden for this kind of case, there are still differences in the distribution. So this really has to be taken into account. And so the point is that there are mostly largest differences between the nucleation process between CAMA and MAM. I already said that we're saturating in the largest bins, but the choices of injection location and material changes, the material changes the outcomes of our size distribution and the burden, and therefore the effects of SIA. And that illustrates that we really need to reduce the uncertainty and improve our aerosol models if we want to run this stratospheric aerosol interventions. So as conclusions, I hope I'm good in time still. So the sectional aerosol model can be used as a benchmark, I would say, to improve potentially the performance of aerosol size distributions in the troposphere and the stratosphere. We also think that, we have to continue to develop this because we just started with some kind of size distribution, but we think for our applications, we need to fine tune this model to get better results still. But really for stratospheric aerosol interventions, thinking about this plot, how much cooling can we achieve? It is important to reduce the uncertainties through improved aerosol models, or at least understand that the effects can be quite large. So potentially, we're much more realistic in a smaller cooling when we use a sectional aerosol model than what the modal aerosol model uses. But this is what all the current simulation have been based on in impact studies. So there's a lot more work to do to reduce the uncertainty. And with that, thank you for your attention.
Great talk, Simone, and thanks for your continued work on this. And it's great to see you presented. Hope I don't steal Ken's question here. But I'm kind of thinking like Ken right now and being like, all right, well, if we're going to ever do this, we need to know pretty darn well what's going to happen. And so there's like, you know, when I see factor of like 30% or something differences between these, factor 2, like how can we move forward in really sort of ramping that down? What can we do to constrain the parameter space so that if we ever do get global governance and this happens, that we know?
Well, yeah, this is one reason why we did this, because we were thinking that how well do we know, or what's even the effect on aerosols, right? If we change to a different aerosol scheme, you need to get trust in what aerosol scheme is more reasonable, obviously. You compare to the observations. If you convince yourself that, say, the sectional aerosol model is much better reproducing observation, you probably trust it better. So you would say that probably we're not going to get that much cooling as the modal aerosol model suggests. And that means, though, you need to run expensive models, right? And then when I see all these talks here, how do we get all this comprehensive aerosol details into the global modeling, right? And one was, how can we make a sectional model more affordable? Yes, we have stronger, bigger computers, we can run more, but it still it's only 2-degree resolution. You know, you have to cut back on some things. Thank you.
One thing you didn't talk about, but I think might be important, is the vertical resolution. Sedimentation is a big factor at the tail of the distribution, and it's incredibly diffusive because in a numerical scheme, because it's very slow. But you're anyway, you know, yeah. So did you look at that effect of vertical resolution?
And horizontal resolution? Oh, vertical.
Vertical resolution, yeah.
Yeah, no, all these, I mean, all these models have the same vertical resolution, at least internally, and I mean, in the CSM framework. However, that's something we can do soon because we do work on a new model version for CSM that will increase the resolution. It will, I'm not sure if that matters too much, but it will almost double the resolution around the tropopause. So that could be an important thing. We did one study where we had a model webcam with 110 layers, but that was a modal model. We did see differences also in the performance. Actually, it would perform better. It would need less injection for the same cause because you had less exchange. So the exchange between troposphere and stratosphere matters and all these things.
Yeah. But it's also throughout the stratosphere. It's very, it's the key factor in determining the injection strength needed because it's the loss term. And for example, you can have a column model as a benchmark and see what happens to your modal distribution for the sedimentation. I bet it's really quite flawed. And that would be my suspicion.
Yeah. I mean, definitely. It's just one little
have a moment of the distribution that's proportional to sedimentation loss, and that would clean that up quite a bit. But
Next speaker is Samuel Frederick, a graduate student at University of Illinois, Urbana-Champaign.
Good morning, everyone. My name is Sam Frederick. I am a second-year master's student at the University of Illinois, where I'm advised by Dr. Nicole Reamer. Today, I'm going to be talking about the impact of emissions spatial heterogeneity on CCN activity. So I'd like to first start out by defining what we mean by structural uncertainty in aerosol models. And the way I'd like you to think about that is by considering a scale or a range of aerosol model resolutions. So on the left-hand side here, we have coarse resolving models. So this might be something like a global climate model that's coupled with a modal aerosol treatment. This might be something like E3SM. And on the right-hand side, we have a large eddy simulation. These are fine resolving models. So a large eddy simulation is coupled with a particle resolved treatment. So we're able to explicitly resolve the large scales of turbulent transport, as well as the compositional diversity of the aerosol particles. And so in the inner comparison of these model scales, we have structural uncertainty. If we want to compute things like the CCN concentrations, the aerosol optical properties, et cetera. So it's a challenge in trying to compare various aerosol model scales. Now, in addition to the impacts of how we're representing aerosols, and of course also the transport of species within our domain, we have impacts of emissions to structural uncertainty. And now the way I'd like you to think about this is if we consider the processes that are occurring within the boundary layer, we have drivers of the surface, so these are emissions that have a certain spatial configuration to them. And so they will be continuously mixed throughout the boundary layer via convective and turbulent transport of the aerosols and the gases. We then have subgrid scale processes that are occurring for the aerosols. So these depend on things like the number concentration, the composition of the aerosols, and then that in turn, the properties of those aerosols will then have impacts on things like the cloud properties. So how hygroscopic the aerosol will determine whether we have more or less CCN activating. Now we know that emissions are certainly very heterogeneous. As an example of this, I'm showing ammonia emissions on the West Coast. We have, this is from the Edgar data set at 0.1 degree resolution. We can see how if we zoom in on Davis, California, there's quite a bit of heterogeneity in terms of the emissions. We have more ammonia emissions near the Central Valley. And the main takeaway that I want you to get at from this slide here is that typical global climate models or even regional scale models are going to have pretty coarse resolution, 50 kilometers or even coarser than that. And their emissions are going to be uniformly distributed across those grid cells. This is something that Jeff Pierce mentioned in his talk. And so the underrepresentation of the spatial heterogeneity of these emissions is going to have an impact on the sorts of properties of the aerosol that we are modeling. So what we're interested in finding here is a relationship between the CCN activity and the spatial heterogeneity. So we can think about this as on the y-axis, the error in CCN activity. This is relative to a uniform base case that is essentially representing what we might have in a regional or global climate model. And on the y-axis, we're going to quantify the spatial heterogeneity within our computational domain, ranging from pretty heterogeneous to more spatially homogeneous. And so we expect to see some sort of relationship, maybe as we go to more homogeneous cases that our error is going to tend to zero. So the way that we're going to go about doing this is using, as I alluded to earlier, we're going to use a large eddy simulation model that's coupled with the particle resolved aerosol modeling approach, part MC. And my lab mates did a pretty good job of explaining part MC earlier, so I won't really belabor the point other than to just say that particle resolved models, they allow us to simulate the per particle aging, and this is going to be highly dependent on the properties of the aerosol. So things like the hygroscopic properties of the aerosol, this is something that is really a benefit of having this particle resolved approach. And also, in addition to that, the reason why we're using this really high resolution computationally demanding approach is that it'll allow us to have a benchmark. If we're using this LES particle resolved approach, we can use that as a benchmark against coarser resolved approaches to then understand what the sorts of structural uncertainty there are in CCN activity. So we're using the coupled Whorf-Pardency model for the particle resolved LES simulations. This is, we're using chemistry that's being run by Mosaic. And we're using gas and aerosol initial conditions that are specified via Reamer et al. 2009. This is a urban plume emission scenario. So our domain here is 4 kilometers square in the horizontal with 40 grid cells. So we have 100-meter resolution. And then in the vertical, we have 2 kilometers, or it's 2 kilometers in height with 100 grid cells. And so the first thing we want to do here is quantify the spatial heterogeneity within our domain. And you might think that, okay, we can maybe just use standard deviation or variance as a measure of the spatial heterogeneity within our domain. However, what I've shown here is 3 cases, if we're looking kind of top down in our domain, of the emissions where we have varying patterns. So on the left here, this is kind of more homogeneous emissions. On the right is fairly heterogeneous. And all of these cases have the same variance. So variance is not really a good measure of heterogeneity for our use case. What we've done is come up with a novel approach to measuring spatial heterogeneity. And essentially, this is a normalized measure of how the variance of a quantity, in this case, the emissions of gas or aerosol phase species, are arranged over our domain. And the way we're doing this is by summing up the difference between the mean of these subarrays. And I apologize, the little subarray squares are not shown up here, but you can imagine that if we have subsets of our domain here that are kind of what our subarray is. We take the difference, the absolute value of the difference between that and the mean over the entire domain, sum that up over all of our subset cases, and that gives us a measure of the heterogeneity of our domain. Now, for relatively large domains, this is quite computationally intensive, so we use a Monte Carlo implementation to estimate spatial heterogeneity. Now we're going to use a variety of spatial heterogeneity cases. We're going to compare all of these scenarios against our uniform base case, where we're emitting everything uniformly across the domain. That is essentially, again, the sort of the GCM regional scale model approach. And then you'll see that the color scale here is changing a little bit as we go from these, scenario 1, where we have relatively low spatial heterogeneity, up to scenario 7. And that's because we're essentially squashing down all of our emissions into a smaller and smaller region. Now we want to quantify the error in the CCN activity for each of these scenario emissions cases. So the way that we're going to do this is first by calculating the critical supersaturation with kappa color theory. So we look at the individual species within each particle, look at how that adds up to the overall hygroscopicity of the aerosol, and then we group the particles by their critical supersaturation and calculate the CCN concentration. So we're grouping them into 0.1%, 0.3%, 0.6%, and 1%. We then compute the average CCN concentration within each vertical level and each time step of our simulation, and then calculate the percent error of those CCN concentrations relative to what we have in the base case. And now we're ready to actually show what this relationship looks like between the error in CCN activity and the spatial heterogeneity. What we see here, we're looking at a relatively low critical supersaturation of 0.1%, is that if we look at higher and higher emissions spatial heterogeneity here on the left-hand side, that we have lower concentration, a lower total number of CCN that are activating. And so you might think, okay, what are the reasons why this is happening? And again, Jeff Pierce did a really good job of explaining one of the reasons why we move from a dilute emission scenario to a relatively compact emission scenario. That coagulation is going to be increasing. It's quadratic in nature. So as we increase the heterogeneity of our emissions, we would expect to have much more coagulation. And what I'm showing here is the percent difference between the uniform base case and each of these scenarios, these model runs for different spatial heterogeneities. And this is the total number of aerosol particles that have coagulated for a given time along the x-axis, and z is the vertical axis here. And this is a benefit of the particle resolved approach, is that we can directly measure the number of particle or a number of coagulation events. So we see that coagulation is decreasing the number of particles that are activating as CCN. Here I'm showing the percent difference for the total number concentration of particles with diameter larger than 50 nanometers. So it's those particles that are most likely to activate. And so this is looking at for a relatively highly heterogeneous case that we have about 5% less particles in the upper boundary layer here that can activate as CCN. So this might be, explaining at least in part this phenomenon that we see where we see less CCN. Now, we also are likely to see impacts of chemistry on spatial heterogeneity. And as an example of this, we see that sulfate, as we go from their scenario 1, which is relatively low spatial heterogeneity, up to scenario 7 with high spatial heterogeneity, we actually have more sulfate in our highly heterogeneous cases by about 3% or so is the increase here. And so this is interesting because we're seeing sort of a competing effect of more sulfate. We would imagine there are aerosol particles are larger, and that means that they're also more hygroscopic. So we might expect to see more CCN that are activating in this highly heterogeneous case. So this suggests that there might be kind of competing effects of chemistry and aerosol processes like coagulation that are occurring. I don't have a lot of time to go into the aerosol chemistry impacts here. This is just kind of show that we have these competing effects. Now, key takeaways. So we see that CCN activity tend to decrease with increasing spatial heterogeneity. We saw that coagulation increases with spatial heterogeneity, and this is likely reducing the concentration of CCN. And so what this means for model linear comparisons and coarser resolved models, so regional and global models that are assuming these uniform emissions cases may overestimate CCN activity in geographic regions that have high emissions heterogeneity. However, I'll caveat that with saying that that intercomparison between our modeling approach and a coarser resolved approach would really require much more in-depth analysis of more physically representative emission scenarios. And yes, so I think I'll stop there and thank you. And if you have any questions.
Hi, thank you. Very nice talk. You could tell by all the hands going up. So you were addressing emissions of chemical constituents. Did you also look at same moisture and latent heat fluxes in their heterogeneity?
Yes, so for this scenario, we're just using the same moisture and latent heat fluxes. We're essentially just taking the LES test case from WRF and applying that for all of our scenarios. However, that is absolutely something that is certainly worth looking at. How that impacts the the turbulence within our domain, and also the other impacts on the heterogeneity, the chemistry that's occurring. Yes.
Yeah, so that's exactly it. And there have been papers on that in the past.
I love this. I've been wondering if we can distill emissions heterogeneity down to 1 or 2 parameters, and just cool to see this happening, and that you can get these results. Obviously, there's a lot of dimensions we need to test, but I was curious to if you, what you were assuming for your boundary conditions here. Were you doing wrapping boundary conditions or was stuff just leaving? And did you have anything flowing in? Because I'm wondering if like what the sensitivity is to that in terms of if you're emitting into something that's already polluted versus clean.
Yeah, so we're assuming periodic boundary conditions here. And yeah, we don't really have any large scale forcing. We just assume, initial uniform distribution of aerosol particles that have a mixture of, I want to say, ammonium sulfate and primary organic aerosol.
So your plume's going to come up and then wrap around and then go back over your source, or I guess if there's that sort of thing. Okay, so it could depend on how long you run it. Eventually, the whole thing's going to kind of.
That's true. Yeah. As we run this for longer and longer, we're going to see a more thorough mixing of our domain.
Okay, thanks so much.
Yeah.
If I understand correctly, you've calculated CCN activity, but you haven't calculated the cloud drop formation.
Correct. Yeah. So
I
we're just
think
looking
that
at
would be
CCN activity
worth
here.
exploring because there's another nonlinear function there that's dependent on concentration that flattens at high concentration. So that really will feed into heterogeneity as well. I think it will amplify what you've already shown.
Mm-hmm. Yeah, certainly at each stage of this, process, we go emissions to the aerosol processes to the cloud processes. That there are all of these nonlinear, effects that are going to amplify or dampen out these impacts of heterogeneity.
Our next speaker is Jiachen Knut, is a graduate student from Drexel University. He's going to tell us about the hyperdual-step method in CMAQ.
Great, thank you for the introduction. I'm honored to share my research a little bit. And we'll just dive right in. So we're applying the hyperdual-step method in the community multiscale air quality model for the assessment of aerosol formation from volatile chemical products. So just to give you some background, volatile chemical products such as personal care products and coatings have become a major concern for human health due to direct VOC exposure and also secondary organic aerosol formation because of these VCPs. Salzen et al. Found that VCPs contribute to approximately 10% of the population weighted SOA mass in continental US. And further reducing the PM 2.5 concentrations in the US requires a deeper understanding of VCP emissions and also its SOA contributions, basically to SOA contributions and PM 2.5. So Salzen et al. Developed a new framework called VCPi to estimate the VCP emissions in continental US. And they found that the average per capita emissions from VCPs are approximately 9.5 kilograms per person per year. And this new framework that was developed by Salzen, the nationwide total is broadly consistent with the UPA's 2017 NEI. However, county level and categorical estimates can be different. So shown on the right is a figure from Salzen et al.'s paper, and it is the county level per capita VCP emissions. So from here, we're going to shift the gear a little bit, and I'm going to talk about what we have discussed, what we have developed. For CMAQ, it is called CMAQ HYD. It is a novel sensitivity analysis method in CMAQ. So we have applied the hyperdual-step method in CMAQ to generate this novel augmented version of CMAQ. And this model can compute the first and second order sensitivities of output concentrations with respect to input emissions to machine precision. And we apply the model to assess aerosol formation from VCPs in CMAQ. So I want to dive into a little bit about the math here, and I'll just show you how we did this and why hyperdual numbers can be used to compute first and second order sensitivities to machine precision. And the hyperdual number H was defined by Fike and Alonso in 2011 as this right here. And here the A's are basically real numbers and the epsilons are non-real parts. And the key property of hyperdual numbers is that the squares of the three non-real components, the epsilons, are zero, while they are not equal to zero in the real space. There are three properties here, but the most important one, I guess, is that their squares are equal to zero. This is a little bit counterintuitive, but just think about this as a special type of complex number, similar to the imaginary number where I square equal to -1, while I doesn't equal to anything in the real space. So we can do this exact calculation of derivatives with hyperdual numbers. And for example, suppose we have a function of interest f of x. We then multiply the variable of interest by this specific hyperdual number HA and expand with Taylor expansion. Then we get this somewhat intimidating equation right here. But no worries, we're going to especially focus on the higher order terms. And because of our definition of hyperdual numbers, we can eliminate a lot of the terms in this equation. So remember we have the hyperdual, so I have put the definition of hyperdual numbers and its properties here. Then if we consider this, basically this square right here, we can expand it as like similar to real number operations. Then we can observe some of the terms here. Some of the terms contain epsilon1 square and some of the terms contain epsilon2 squares. So because of our definition of hyperdual numbers, they're 0. And if we consider the higher order terms, like the x1 epsilon plus x2 epsilon2 to the third, all of the terms contain epsilon1 square or epsilon2 square. So all of them are 0. So essentially, the higher order exponentials in this form will all be 0. Then we can basically go back to the Taylor expansion and found that, oh, we have all the higher order terms that contain like order greater than or equal to 3. They will be 0. And we'll get this equation right here, which is, notice here that for regular Taylor expansion, we usually have the approximately equal to, but in this case, it is actually exactly equal to this term here. So basically what we have is that the real value, which is f of x, and the first order derivative, which is this f prime of x term, and the second order derivative, which is this f double prime of x term, they're separated into different terms of hyperdual numbers. And because we can eliminate all the higher order terms, what we get from this is basically exact. So to implement this method, we developed a new hyperdual operator overloading library in Fortran. And so here is just one example of addition of two hyperdual numbers. And the addition is pretty simple. You add, so the notation here is a little bit different, but you add basically the real parts, epsilon1 part and the epsilon2 part and the epsilon1, 2 parts. Over 400 operations involved in the chemical transport model, in this case CMAQ, are defined by this operator overloading library. And these operations are tested offline for their accuracy in both real number calculations and also sensitivity calculations before being applied to the chemical transport model of interest. So now we can put the puzzles, put the puzzle pieces together, and we have the HT mod, which contains all these hyperdual operations. Then we have CMAQ, which takes in emissions. It only has some examples of emissions and concentrations. They go through physical chemical processes and atmospheric transport. And in this case, we have the Atkin mode nitrate, Atkin mode accumulation mode nitrate, and also an aerosol phase monoterpene nitrate products right here. Then we combine them to form this new CMAQ HYD model, which basically I colored everything in purple. And in addition to the emission inputs, basically what we need to do is to perturb the emission of interest in the hyperdual space. Then we'll be able to get sensitivities of all the output variables with respect to the input variable that we perturbed. And there are some source code modifications here. I'll just discuss about the source code modification a little bit. So for example, here we have the vertical diffusion in CMAQ called VDiff. So the only change the source code is actually changing the real variable of interest to be hyperdual. So in this case, we use the hyperdual mod. And so this C-grade variable, which is basically the concentration of species in CMAQ, we change it from, it used to be real type, we change it to be the newly defined type hyperdual. Then we basically start from there, and everything that depends on this C-grade variable need to be hyperdual. In this case, not all the variables in the model need to be changed to hyperdual. This is basically done to reduce the computational overhead of the augmented model. And a typical CMAQ HYD run in the regional scale is approximately 2.5 times as expensive as the original CMAQ model. So it is not as bad because we get these additional information, which could only be retrieved by running the CMAQ model multiple times. So here we have the CMAQ model, and one key thing that I want to point out here is that the real concentrations are unchanged, and we get additional outputs which contain both first and second order sensitivity information. So in this case, we want to play around with the model by modeling VCP contributions here, and we have different emission sources. So we basically set like the graded emissions used to contain the VCP emissions, but we need to separate the VCP emissions to form a new graded emission file. Then we perturb the VCPs, then we get all these sensitivities in addition to the regular concentrations. And so before diving into the results, I want to reiterate some of the physical meaning of first and second order sensitivities in these models. So the first order sensitivities are usually easier to understand. They describe the slope of the relationship. And the second order sensitivity basically describes the curvature of the relationship. Since many processes in these chemical transport models like CMAQ are highly nonlinear, understanding the second order sensitivity is usually important. So basically, if you only consider first order sensitivities, you are basically drawing tangent line on these emission to concentration relationships, and you will either underestimate or overestimate the effect of certain emission on the concentration of species. So here's just a proof of concept CMAQ HYD application with VCP emissions. We run the model for 12 hours. The domain is the continental US grid. And here I've shown the concentration of PM 2.5 in the regular model run and the hyperdual model run. You can see there the real concentrations doesn't really change. And here are some of the sensitivities. So all the sensitivities I've shown here are semi-normalized, which means that they're normalized based on the emission of species. So you can see it is the concentration of certain species with respect to the percent change of the emissions. So in this case, we have a specific monoterpene nitrate product. So it depends on both VCP and NOx emissions. And as you can see, most of the values are positive here. And this is the nighttime formation of accumulation mode, monoterpene nitrate aerosols. And it depends on both monoterpenes and VCP and NOx emissions. We also have the total PM 2.5 with respect to VCP and also NOx. And this case is a little bit more interesting, especially for the VCP case. You can notice here in central US, we get negative first order sensitivities, which means that if there's an increase in VCP emissions, there will be a decrease in the total PM 2.5 concentration in the area. So one possible hypothesis is that VCPs react with nitrate to form this aerosol nitrate products, leading to less ammonium nitrate formation, which leads to a slightly negative sensitivity of PM 2.5 concentrations to VCP emissions. So the real strength of our model is that it can compute higher order, or in this case, second order sensitivities to machine precision. So we still have, in this case, the AMTNO3 concentration with respect to VCP and NOx emissions. We have the second order stuff right here. So from here, you can see the second order sensitivity of aerosol phase monoterpene nitrate products with respect to VCP is pretty much 0, while it is especially prominent in southeastern US with a negative second order sensitivity. So basically, we have an increasing but concaving down relationship between NOx and total PM 2.5 concentration in the area in southeastern US. So this information cannot be retrieved usually accurately with traditional approaches. And here we have the total PM 2.5 here. Still the VCP has some nonlinearities in some of the big cities, but the nonlinearity is pretty small, but the nonlinearity of total PM 2.5 with respect to NOx is pretty interesting. And it is somewhat scattered in a sense. And if the second order sensitivity is positive, it is basically a concaving up and also increasing relationship. If it is negative, it is a concaving down, but still increasing because we have first order sensitivities greater than 0. So our model can also compute the cross sensitivity, which basically describe the synergistic effect of of multiple emission species. So in this case, what I want to highlight here is that, since I'm running out of time, is that actually the cross sensitivity of PM 2.5 with respect to NOx and VCP are positive, which means that an increase in NOx emissions will increase the effect of VCP on total PM 2.5. And it also works the other way. So in conclusion, we have developed an augmented version of CMAQ, which can compute first and second order sensitivities to machine precision. We plan to run monthly simulations across different seasons. We also plan to evaluate the health-related impact of VCP emissions based on the calculated sensitivities. And in theory, the hyperdual-step method can be easily extended to other numerical models where sensitivities are of interest. I have this QR code here. It is a GitHub repository. If you're interested, you can just download it. And here are the acknowledgements, and thank you for your attention.
This is really cool. Try to follow along with the math, but mostly following along with the punchline. So I missed though what time period was this? Was this winter? Because I was surprised at how ammonium nitrate dominant the whole, like even down south was.
Yeah, it is during the winter.
Okay. So what would you expect would happen if you did the same test during the summer?
Are you referring to a specific set of sensitivities?
Like the same stuff you were showing with the sensitivity to VCPs versus the sensitivity to NOx. Like I was just thinking you'd be much less NOx sensitive in the summer because you're not going to get ammonium nitrate in Houston, way down south and that sort of thing. So when it's really hot.
Yeah, so we would definitely try to run the model in summer in the near future, but I think yeah, so we'll try to run the model in the summer to see the effect. So I wouldn't say the sensitivities will be larger or smaller, but like you can kind of predict the concentration of PM 2.5 and like nitrate, ammonium nitrate in the southeastern US. But in terms of sensitivities, I feel like it is a little bit harder to say for sure. So yeah.
Jiachen, in a lot of other sort of sensitivity applications for PM 2.5, we'll often say, we think the PM 2.5 is sort of linearly responding to NOx changes on the scale of, NOx emissions changing up to 10 to 20%. Now that you have both the first order and second order sensitivities right here on the same slide, is that range sort of supported by the magnitudes that you're seeing here? Or can you help us better refine like over what range we'd expect a linear response of PM to NOx change?
But I think basically from this figure, you can see, I mean, the nonlinear response of NOx to PM 2.5 is pretty prominent. But like in this case, the VCPs are pretty much linear in this case. So
I guess this plot is a factor of 10 smaller.
yes.
Okay.
So over, I guess, larger ranges, the nonlinear effects are going to be more prominent.
Yeah, very interesting talk. So I want also kind of ponder a little bit on this figure here. So your top right basically shows that increase of NOx related to the increase of PM 2.5 for the most part because it's positive. But on the bottom right, you see a lot of variations. Some are, so my question is that are you showing the sensitivity of the PM 2.5 to the NOx emission factors at the local, each grid box? Are you able to see, for example, the transport? Because the sensitivity of the PM 2.5 in one location can also amenable to the change of the emissions in other places, in upwind places, right?
Yeah, so this is a grid like domain-wide
Local.
perturbation. So this is based on a domain-wide perturbation of NOx in this case, and CMAQ does all the transport stuff within it. So it is the sensitivity of the local cell with respect to the perturbation of that local cell.
So this is local within, okay. But your model can calculate the, like the sensitivity to the concentration in one place to the change to the emission in other places, right?
Yeah, in that case, it will just perturb the emission in some other places, and what you get, so you can perturb, say, only one cell.
Okay.
Or like a point source in this case to see its effect on the surroundings, because CMAQ does all the transport, and you'll be able to see the sensitivities to that specific emission source.
Will be interesting to see which one has the most largest secondary derivatives of PM2.5. This is NOx.
Yeah, I mean, NOx is definitely has a pretty large second order sensitivities. I feel like it's the inorganic species mostly. Yeah.
Thank you.
Okay, our final speaker of this part of the session, before we take a break, is Megan Nalasso. She's a PhD student at Columbia University, and she's going to tell us about estimating radiative effects and constraining the free parameter space of brown carbon aerosols in the GISS model.
All right, thank you so much. I'm just going to jump right in and do a brief summary of my previous work. It's going to be very brief, but if you want to read more about it, you can see our recent preprint in ACPD. So my previous work was introducing brown carbon, which is an absorbing organic aerosol, into the GISS ModelE or system model. We did this by defining 4 key properties or processes in the one moment aerosol module of Model E. So firstly, because brown carbon aerosols are emitted by biomass burning, we designate 35% of biomass burning organic aerosol mass to be brown. So we set a brown carbon to organic aerosol emissions ratio. We also know that biogenic SOA can be brown, so we attribute absorption to pre-existing isoprene and alpha pinene tracers in the model. And then to actually attribute this absorption, we assign non-zero imaginary refractive indices to all of these brown carbon tracers. Specifically for primary brown carbon, we find a reasonable range of imaginary refractive index values, and then we use that midpoint. And then finally, we designed a chemical aging scheme so that primary brown carbon would be emitted into the atmosphere and then browned and bleached. So all of these parameters considered together make up what we call our base case representation of brown carbon, which is kind of our starting off point. Using that, we were able to estimate the top of atmosphere annual average brown carbon direct effect to be 0.04 watts per meter squared, which is within the range reported by other ESMs. And then we conducted sensitivity tests in which one of the 4 of these brown carbon properties were varied at a time and compared to our base case, just to try to see how they would change this brown carbon effect. These tests told us that including SOA as brown and having a chemical bleaching scheme do have distinguishable effects, but varying other properties, including browning, actually don't. So we weren't able to narrow our reasonable range of imaginary refractive index values used or our emissions ratio. Finally, in this work, we evaluated the model with this brown carbon scheme included by comparing model output of total AOD and AOD to that of AeroNet and MODIS. This showed us that there was limited to no difference in model performance with and without the brown carbon scheme. So essentially what this work did was it created a brown carbon scheme, which created a large free parameter space, but we were ultimately unable to constrain that space. So that brings me to the work that I'll be talking about today, which is evaluating our scheme with brown carbon data. We're using 2 main approaches to do this. First, we're using a retrieval of brown carbon properties from AeroNet performed by Greg Schuster. Briefly, Greg uses a bimodal retrieval algorithm, taking size and complex refractive index and producing information about an internal mixture of non-absorbing organic aerosols with absorbing inclusions of brown and black carbon. This retrieval produces data of column burden, as well as brown carbon AOD and AOD, which we can use for our comparison. And then our second approach is comparing our scheme to in situ measurements of brown carbon absorption from multiple flight campaigns. These typically produce absorption in inverse length at 365 nanometers. So starting first with the AeroNet retrieval of brown carbon properties, We use annual fire carbon emissions within biomass burning regions to try to identify a year with a lot of fire activity. So we do this because we know brown carbon is produced from biomass burning. We want to make sure that our aerosol properties are well captured around fire events. So as an example, we can look at Southern Hemisphere South America, and we could identify the year 2010 as a year with a lot of fire activity. Then we look back at the retrieval data set, and within that region and year, we look for a site and period that has good data coverage. So as an example, we identify the Alta Floresta site from July to December of 2010 as a site and period of time that we want to zoom in on further. So this is showing a comparison of Model E simulated to AirNet properties. So it goes from brown carbon AOD, AOD, brown carbon column burden, and then the ratio of brown carbon to total organic mass, with the purple line here showing model simulated properties and the black lines showing the AirNet retrieval. And this is over that selected site. So what we're seeing here is that the model seems like it's overestimating brown carbon AOD in mass, but getting closer in magnitude to brown carbon AOD. We repeated this analysis in multiple regions at different AirNet sites, and we found pretty consistent results, which led us to this initial finding that there's an apparent inconsistency between retrieved brown carbon AOD and AOD and what we simulate in our model. Model E seems to overestimate AOD in mass, but gets closer in magnitude to capturing brown carbon AOD, or sometimes vice versa. So what this is beginning to tell us is that Model E doesn't seem to simulate as much brown carbon absorption with the same amount of mass compared to this retrievable data set. To try to address that inconsistency, we looked to the assumptions in brown carbon treatment that went into Greg's AirNet retrieval. And actually looking at these assumptions, we're able to constrain 3 of the 4 brown carbon properties that we introduced into our scheme. That's because the AirNet retrieval has one key assumption, which is that there's one constant imaginary refractive index for brown carbon. That value is higher than the value we used, and it also eliminates the inclusion of secondary brown carbon, so as SOA is brown, and it eliminates a chemical aging scheme. So the 4th property we weren't able to constrain with AirNet assumptions is our emissions ratio. But by looking at our initial site comparisons, we can see that mass tends to be overestimated. So we can infer from this that maybe our base case ratio of 35% is too high. So using these assumptions, we designed a revised simulation in which parameters were adjusted to match that of the retrieval. And then we also applied an absorption enhancement factor. So we did this because AirNet retrievals in general assume an internal mixture of aerosols, but the IAMA module that we use within Model E uses an external mixture of aerosols. So in order to adjust for this, we add this absorption enhancement factor to mimic brown carbon being mixed with a non-absorbing organic aerosol. The goal of this simulation, obviously to be brought closer to the retrieval data set, is to reduce brown carbon mass and therefore AOD, while simultaneously increasing mass absorption efficiency. So this shows that same comparison at that same site over Alta Floresta, where our top row is showing what we saw previously, and the bottom row is showing the results of that revised case that I just described. What we can see here by comparing top to bottom is that we seem to have greatly reduced aerosol AOD and mass, bringing them much closer in magnitude to the retrieval. We also do see a slight reduction in brown carbon AOD, but the magnitude of that reduction is much smaller compared to how much we were previously overestimating those other variables. So we repeated this analysis again in multiple regions at other sites, and we came to these initial conclusions that by resolving these inconsistencies in brown carbon treatment, we were able to actually bring our simulated properties closer to this retrieval of brown carbon properties. It's really important to note here, however, that a retrieval is not the same thing as observations. We can't say that the parameters in this revised case are the ground truth. We can just say that by adjusting these parameters, we were able to get it closer to this retrieval data set. In order to further constrain this, we want to actually look at in situ measurements of brown carbon absorption. So we started doing this, firstly looking at in situ brown carbon data from the DC-3 flight campaign. This took flight measurements using a DC-8 aircraft over the United States between May and June of 2012. And this map here shows just the large breadth of brown carbon absorption data that was available from this campaign. We've added boxes around the 3 subregions here. These were identified by Barth et al. As 3 distinct chemical composition environments. So we're using this to guide our analysis. Just to briefly characterize these, the first region is northeastern Colorado. It's influenced by an urban corridor, as well as agricultural and ranching activities. It is characterized by Barth et al. As having moderate to high anthropogenic VOCs and low BVOCs. The second region is central Oklahoma to West Texas. This has the sparsely populated southern Great Plains, influenced by agriculture, pasture, and grassland, as well as a metro area that affects central Oklahoma. So this has low to moderate BVOCs and low to moderately high anthropogenic VOCs. And then finally, we looked at northern Alabama, which has a highly forested region resulting in high BVOCs, as well as some regional urban sources producing anthropogenic VOCs. So using these regions and this data to guide our analysis, we created vertical profiles comparing DC3 measured brown carbon absorption with what we simulated in the model at the same times in each of these subregions. So campaign data was first gridded to the model's spatial and temporal resolution, and then both campaign and model data were averaged within each subregion over the entire measurement period. The shaded areas on each graph are showing you 1 standard deviation of data. We also display in each of them the linear regression, just comparing the 2 vertical profiles to each other. And then finally, these blue bars here on the right show the number of data points to average to actually get these vertical profiles. So if we look at this overall, keeping in mind the very coarse resolution we're working with in Model E and the fact that sometimes we have limited campaign data, the model actually seems to align pretty well with flight campaign measurements. Zooming in on each of these regions, we can see in central Oklahoma to West Texas, when we have a good amount of data, the model actually aligns pretty well with the DC3 measurements. Looking at northeast Colorado, when we have a lot of data, it seems to have a little bit of underestimation, so it doesn't align as well. And then finally, looking at northern Alabama, this is where we're limited the most in terms of data, but we do seem to be seeing an overestimation of brown carbon absorption by the model below the boundary layer. So the next question I wanted to ask was, what if we applied that same analysis that we did for AeroNet sites, but to sites within these regions? So this is very recent analysis. I just wanted to get an idea of what we could look at here, but I had to use model output that I already had. So it's not the same year as the DC3 campaign, but it's the same time of year. I also wasn't able to do this over northeastern Colorado, just because the AeroNet sites I had at that time didn't have enough data. But what we're looking at here is the same analysis I showed you previously, but this is over a site in the central Oklahoma to West Texas region. And if we zoom in on brown carbon AOD, we can see that where we have retrieval data, similar to the DC3 campaign, the model does seem to align pretty well in magnitude with what we're getting in terms of retrieval measurements. And then this can be compared to a site over northern Alabama, where similar to biomass burning regions, we seem to be overestimating a lot of these variables. But we also seem to be overestimating brown carbon AOD. And we also saw that in our DC3 vertical profile comparison. We saw a little bit of overestimation in brown carbon absorption. For this one, it was really interesting. If we then look at our revised case where we've removed consideration of secondary brown carbon, we see brown carbon absorption and brown carbon mass actually improving in comparison to the treatable data set. So what this is beginning to tell us is that our isoprene SOA, which is really prominent in this area, within our scheme might be either too brown, or we might be attributing too much SOA mass to brown carbon. So obviously this is really early work. We're just kind of starting to explore this, but what are we seeing and where do we go from here? Well, with this DC3 analysis, as well as this comparison to retrieval data, we're beginning to see regional differences in needed brown carbon representation emerging. We're going to continue exploring this specifically with DC3. We want to look at co-located data to try to understand what may be driving these differences. So what's going to be really helpful to look at is total water-soluble organic carbon mass, the mixing ratio of volatile organic compounds in these regions, and then also number fractions of aerosols from different sources. We're also going to repeat this analysis looking at other flight campaigns. The benefit of this being that we can look at brown carbon in different regions produced under different conditions. For example, the FireX and WeCam campaigns actually look at fire plumes, so we can study that, whereas the ATOM flight campaigns will hopefully give us an idea of brown carbon in the remote free troposphere. Okay, these are my acknowledgements. I'd love to take any questions you have.
Great talk, Maggie. Thanks for this. And my question's out of curiosity because it's something my group is struggling with. So I'm wondering if you've been thinking forward about comparing to WeCan and FireX, where we have these plumes that are much narrower than the GISS grid box.
Yeah.
And you've been comparing a lot of extensive properties like extinction coefficient or absorption coefficient.
Yeah.
And so you're going to have these spikes as it flies through the plumes. In fact, the aircraft transects aren't even going to cover the whole width of a grid box.
Yeah.
So how do you plan to tackle that when you're comparing your coarse grid box to because you're going to underestimate your absorption if you just take your grid box and compare it to that. So I'm just curious if you have ideas because. Yeah.
That's a really good question. Simple answer, I'm not really sure yet. A lot of what I'm doing right now is just kind of exploring things, not just the spatial resolution I'm concerned about. I'm also concerned a little bit about the temporal resolution. I mean, firstly, you have a campaign that can go from one grid box to another because it's literally on a plane, like in a matter of a few minutes. Also, you don't know how fast these plumes are actually moving. Yeah, so there's a lot of limitations when we're working within this. There was a presentation a few days ago or yesterday that was actually looking at the FireX campaign. And so I might try to do something similar to that, whereas trying to normalize it and get a little bit of a baseline to give me a better idea. For example, putting it over carbon monoxide. I don't have a good answer though in terms of addressing the spatial resolution. The closest we can go in terms of temporal resolution for the model is 30 minutes. So I'm going to do my best with that. That's what I've been doing for these campaigns so far. And then we're just averaging both campaign and model data to try to get a vertical profile. Yeah, that's not a very good answer. Yeah, but still there's so much data that it's, I also have scatter plots that I'm not showing just because when you put all the points comparing each 30-minute period together, it's really hard to get like good conclusions from it.
It's a very interesting talk. So I just have a kind of one comment I actually want to hear from you too, is that this brown carbon retrieval from AirNet, how big are their uncertainty? And I would think that I like your comment is that those are retrievals, are not the observations. So even the retrieval, there are secondary retrievals. They are using the single video, which first of all retrieve from AirNet, and then you derive the brown carbon.
Yeah.
So how you try to look at one, compare it directly with the single video from your AirNet? Two, have you tried to look at the brown carbon derived from AirNet versus from aircraft in the first place?
Sorry, can you repeat the last part of the question?
Compare of the AirNet derived brown carbon versus the one that made by the aircraft in the first place.
So just remove the model in the middle and do the direct comparison. No, that's a really good point. I haven't done that yet. You make a really good point that it's a retrieval of a retrieval. There's also a few other issues with brown carbon. When you're looking at absorption data, you can look at these magnitudes. They're really small. Like there are limitations that we get from the AirNet retrieval. So no, I haven't compared directly these properties that we're getting versus flight campaigns. The simple answer is I haven't had time. The more complicated answer is that it's a little difficult because you're looking at different variables. So inherently, you're going to have to add even more assumptions into the mix, right? So this is spitting out AOD, and column burden. And then what we're getting from actual flight campaigns is like filter impacted and then into solution measurements of absorption. So there's assumptions that go into both of these data sets that, I'm trying to work with. I haven't compared them directly yet. I don't know. Yeah, I'm trying to just kind of spread out and look at as many as I can, but it's a really good point. Yeah.
Okay, let's thank Megan again.